All right, can you all see the board and see me and hear me okay?
Yeah.
Okay.
Yeah.
All right, good. Sorry for the delay. Something came up that I couldn't avoid. So what I'm going to do today, just 1 second, I have another technical glitch. What I want to do today is talk about this lab called the Multimeter quiz. And it's going to be due on October 3rd. And it's another video that you're going to create for me demonstrating a skill that you have, basically how to wire a real simple circuit. And really, the circuit is in your lab kit. So you're going to basically learn how to wire this. Okay. And I don't want, and what I don't want to do is show you here how to wire. I want you to think about how to wire. Otherwise, you're not going to learn anything. And then you're going to make some basic measurements with it. You're going to be using multimeter that came in your kit. Oops, I brought the wrong one. Okay, I brought the wrong multimeter. Sorry. Yours is red. Okay, this is not a red one, but they work very similarly. And I'll show you basically how you can measure voltage, how you can measure current and resistance with it. It's pretty straightforward. Most of them are very similar. Mine's a little different. For some reason, I ended up bringing the wrong one. It just where everything is in a dial is different. That's all. But they work the same way. In order for us to be able to understand a little bit about this lab, I need to talk a little bit about what makes the light go on in the circuit. Okay, so for example, if I take, let's see, this battery and connect it to the light bulb, I don't know if you can see that. Light goes on. Now, what's causing that? What are the basic ideas behind how this works? So I guess the first thing to talk about is if I have a wire and I want to run electrons through it so that we make a light go on, what do I need to do? Well, I need an electric field. Because if I have an electric field between the two ends of the wire, if I have an electric field in the wire, that's going to cause the charge to flow in the wire. I'm going to produce a force F equals QE. And if the field's uniform, then it's easy to write the work done. It's really a dot product, but let's assume E and D are in the same direction. Oops. And so the field does work on the electrons. Okay, the field's doing work on the electrons. But what's producing the field? Well, a device called a battery. So the battery, or power supply, is there to make the electrons flow. The battery produces a field between the ends of the wire, or in the wire, let's just say it that way. So the battery allows you to produce a field in the wire that causes the electron to flow. Work is done on the electrons. They now have kinetic energy. The kinetic energy of the electrons gets converted into heat and light energy as the electrons bump into the atoms of the filament. Okay? So we need a battery for this. And you can use the analogy of water flowing through a pipe to try to understand this. And in fact, if you go into modules, I actually put a video in the modules which has the water analog for electrons going through a wire. And so you should watch that. Okay. So a battery or a power supply is what does this. A battery is a device that has energy stored. Okay. So the battery has energy, and the work done by the battery is going to be equal to the change in potential energy of the electrons. Okay. And that's minus the work done by the field. And I'm using stuff from Physics 205 here. Okay. So work is done by the battery, the potential energy of the electrons changes, and that gives the electrons kinetic energy and it allows them to go through the wire. And of course, as the electrons go through a wire, they bump into atoms, and that actually causes them to lose energy. And eventually all their energy is lost due to it's produced into heat. Usually we don't describe the battery in terms of what is the change in potential energy it provides to a system. But what it does is, what we do is we define the battery, or we describe the battery in terms of the amount of energy per unit charge it can deliver. And so we divide this by Q. And we define something called the energy per unit charge. And we're gonna learn more about this in chapter 25. So we define something called the energy per unit charge, and that's called the voltage. And so what a battery is a device that maintains a voltage. And that should be more precise. Okay. Delta U is the electrical potential energy in this case. Okay. Delta U over Q is the electrical potential. This is called the electrical potential difference. Okay. V by itself is called the electrical potential. The unit of this is the volt. And so V is called, we think of it in terms of voltage, although it's a bad term to use because we also use the term voltage for potential difference. So it's a bad term. So I'm going to try to use either potential difference as much as I can, or when you look in the lab, it'll say PD. What's the PD? Meaning the potential difference. And in common terminology, it's the voltage that you would measure with one of these devices. Okay? And so what a battery is or a power supply is a device that maintains a potential difference between its terminals. Okay. So you can think of it about in terms of the amount of work per unit charge it does on the system. Questions on that? Now, the rate in which charge moves through the wire is called electric current. The rate in which charge moves through the wire is called electric current. And so how do we describe electric current? What is electric current? Well, it's just a flow of charge. An example is the flowing of electrons through a wire. You can have a beam of positive or negative charged particles that's produced in an accelerator. You can have charges flowing in an electrolytic solution. Those of you that had chemistry, you've probably done some electrochemistry experiments. You've talked about current there. Okay. The one thing about current is this, that there's no difference between charges moving to the left, positive charge moving to the left and negative charges moving to the right. Whether, if I have a battery, and I'm going to draw the battery like this for now, I'll change it into something called a schematic diagram. Whether this gains electrons okay, whether electrons go this way or positive charge goes this way doesn't make a difference. The current is the same. They're identical. So whether you have positive charge moving to the left or negative charge moving to the right, it has the same effect. Okay? So, how do we describe current? Well, actually, how do we describe current in a wire? So there's two conventions in terms of how we describe current in a wire. Let me draw a circuit. I'm going to put a light bulb in it. The picture you see in the slide doesn't have a light bulb. That's a direct short. That's bad. Okay. For many years, it was thought that in a circuit, positive charge goes from the positive terminal of the battery to the negative terminal of the battery. So the negative terminal would gain positive charge. And the positive terminal would lose positive charge. Okay, and we call that conventional current. We call it conventional flow of current. Now, it wasn't until later, until we understood something called the Hall effect, an experiment was done, and it was realized that current really involves electrons flowing from negative to positive. So if you have electrons going from negative to positive, this becomes more positive, and that becomes more negative. If you have current going in the other direction, this becomes more negative, that becomes more positive, and you see how that doesn't make a difference. So physically, it doesn't make a difference. In fact, when you solve a circuit problem, it doesn't matter whether you use conventional flow or electron flow in trying to solve your circuit. It doesn't matter because the physics is the same. Okay? Now, let's try to say something about current. Current is the rate in which charge flows through some area of a wire. Okay? So let's say we have a wire. I'm going to blow up the wire. Meaning I'm going to make the wire bigger. So here's a wire. And I want to consider how much current or how much charge goes through that area in a time period. I want to know delta Q over delta T. And really this is called the average current. If I want the instantaneous current, then I would take the limit of this as delta T goes to 0, and then I get a derivative. Okay. So I want to learn a little bit about what current is. So I want to see how much charge goes through this area in a time delta t. In a time delta t, how far does charge move? Okay, in a time delta t, how much does charge move? Well, let's say the particles, whatever is carrying the charge, are moving to the right with some velocity v sub d. We're going to call that the drift velocity. So the distance the charges travel in the time delta t is going to be L equals v sub d delta t. Now the volume of charge that passes through this is going to be L times the area of the wire that's the volume of charge that goes through there. But if I know the number of charges per unit volume, then I know how much charge passes through this area. So the number of charge carriers is going to be v sub d delta t a times n. We'll call the number of charge carriers. So that gives me the number of charge carriers, but I also need to find out the total charge, so I have to multiply by the total charge of each one of these. Where Q is the amount of charge on each charge carrier. So that's how much charge flows through here. And I should make this a big Q. So we get delta Q is V sub D delta T A and Q. Delta Q over delta T is our current. And that's how we define our current. Okay? That's our current. In a simplistic way, that's how we write it in terms of the amount of charge carriers we have. And if you want the instantaneous current I is dq over dt. This is an average current. That's an instantaneous current. Of course, I would have to know things. I would have to know what v sub d is as a function of time. I'm assuming the area doesn't change. Okay. And so if I is dq dt, dq is I dt, and q is the integral of I dt. Did somebody have a question?
Yeah, I'm sorry. Well, what does the A stand for?
The area of the wire, the cross-sectional area.
Oh.
Okay, I didn't want to write pi r squared. I was just very general. Okay. So the unit for current is coulomb per second. Another term is the ampere. And the ampere is a pretty big unit. think about how many electrons per unit time go through this area. In other words, 1 amp is 1 coulomb per second. If you divide by 1.602 times 10 to the minus 19 coulombs per electron, that gives you 6.25 times 10 to the 18th electrons per second passing through this area. That's a lot of electrons. So you have a little wire carrying 1 amp of current. That's how many electrons are going through that cross section of the wire. Now, the amp is a fairly large unit, and so we use maybe the milliamp a lot of times, which is 10 to the minus 3 amps, or the microamp. Those are common units. The unit of amp, well, you use it, you see it, for example, when you talk about a refrigerator, microwave oven, appliances. But then when you look at the currents in your computer, depending on where you're in the computer, and if you're looking at the power supply, yeah, you're looking at amps. But if you're looking within the circuit board, it's either microamps or milliamps. Or nanoamps, it just depends if you're looking in the CPU, various parts of the CPU. Okay. Now, how are voltage and current related to each other? How are they related to each other? Well, there's a special case that works. Well, there's a very special case I want to look at. Ohm did an experiment. And Ohm measured current as a function of voltage, or we can. So anyway, Ohm measured current as a function of voltage. Let me use a different color. And what I mean by voltage, potential difference, okay? So my notation was bad on that graph. But that's what's commonly said. So voltage here, potential difference here. And he noticed that for many materials, you get a straight line. So that shows that I and V at delta V are proportional to each other. So if I take a battery and hook it up to some device, we'll call it a load. And I don't know the history behind how he did the experiment, but he was able to see that for many materials, the potential difference and the current are proportional to each other. And their proportionality constant was a slope. I'm going to call the slope 1 over R, where R is the resistance, which is a property of, what's kind of like a property of material, but it depends on several things. It depends on the property of material, but it also depends on the geometry of the material that you're using. Okay. The resistance is really an opposition to a flow of electrons. Okay. Resistance is an opposition to a flow of electrons in your little circuit here. Okay. As a result, we can change, since we know the proportionality constant, we can change the proportionality to a resistance, and we say delta V is I times R. This is Ohm's law. And you should be aware not everything obeys Ohm's law. Light bulbs do not obey Ohm's law in the sense that you get a straight line. You actually get a curve. The green curve that you see in the graph is something non-ohmic, like a light bulb. Okay. Ohm's law is like Hooke's law. Because, you folks learned Hooke's law, right? F equals minus kx. But what if you take a spring and you stretch it too much? Will it obey Ohm's law? Will it obey Hooke's law? The answer is no. Okay? It won't obey it. Okay, because you stretch the spring too much. Same thing here. If you put too big a voltage on whatever your load is, whatever that material is made out of, it's not going to obey Ohm's law. It's because the material is going to get hot. And as the material gets hot, the resistance changes. Just like a light bulb. So the units for resistance is the ohm. Okay, it's the ohm. Or you can use the Greek letter omega. And this tends to be a fairly large unit since current is a small unit. R tends to be a large unit. And so we talk about resistances in kilo ohms. And megohms. And again, remember this is a capital letter omega. And that represents ohms. So how do we make measurements? How do we make measurements in a circuit? So this is the basics of what you need to know about a circuit. You need to know what's pushing the electrons. You can think of the electrical potential difference as the water pressure. You can think of the electric current like the flow rate. Okay, and the resistance would be, you can talk about in terms of something called a conductance or conductivity that affects the flow rate in a pipe. Or 1 over the conductivity would be like the resistance. So that would be analogous to it. Okay. Usually you use that when you're talking about gases flowing through a pipe. So how do we measure these quantities? So one of the things you got to think about is when we measure something, what does that mean? When we make a measurement with a tool, what are we doing? When you're measuring temperature with a thermometer, what are you doing? Well, you take a thermometer, you put it in the water. When the temperature of the thermometer equals the temperature of the water, then you say that's the temperature of the water, right? So the instrument itself has to have the same properties as what you're measuring. Plus, the instrument cannot change the property you're measuring, right? So it's got to be used in a way that you cannot change. So if you make using a thermometer, it's huge. Let's say you make a thermometer out of a big pipe and you put it in the water, that's going to change the temperature of the water. So you make the thermometer small so it doesn't change the temperature of the water. But when the temperature of the water equals the temperature of the thermometer, then you know what the temperature of the water is. Okay, so same thing here. If we're going to be measuring voltage, current, and resistance, or if we're going to be measuring voltage and current, the voltage across the instrument, the multimeter, has to be equal to the voltage across the battery. If we're going to be measuring current, the amount of electrons per unit second going through here has to be the same as the amount of electrons per unit second going through the wire. So how do you measure voltage? That's actually pretty straightforward. And we use the term across. So when you measure voltage, you put your meter, your multimeter, and I'm sorry I'm using the wrong one, across the terminals of, let's say, a battery or across the bulb. So first of all these have a volt input and a common input. So you're going to want to put one in the volt input and one in the common input. Okay. Then you want to turn this to voltage, like so, V for voltage. And then you can just hook it up across the battery. Do I have bad? I wish I had some a camera person here. And you just put it across like this. You put it across the terminals. And that'll measure the voltage. So right now mine says, hold on a second. I don't have it in good spot, hold on. I'm only getting 0.2 volts, that battery's almost dead. Hold on a second. I thought I had a better wire. I'm going to do it this way. Okay. So let me see if I can point my camera down. And get a good connection. Can you guys see the voltmeter? So I'm going to connect.
We can see part of it.
Okay, hold on a second.
It's behind the slide.
Is that better?
Yes.
Okay, so I'm going to put the negative to the negative terminal of the power supply, of the multimeter, and then here's the positive. So now it reads about 1.39 volts. Okay. So basically what I did, if I take the battery, I just put one terminal of the meter here and one terminal of the meter here, one here and one here, and I got a voltage reading. Okay, that's really all I did. Since you got one here, my wire's too short, and one here. For some reason I'm not getting a good connection. Oh, there you go. Okay, that's called measuring across. Another term for across is parallel. All right? Another term for across is parallel. Questions on that? Voltage is easy to measure. It is very hard to screw up voltage measurements. All right, let me point this back up. Okay, let me go to the front board. So if I have a circuit, let's say with a light bulb, so now I'm going to change my picture for a battery because the way I was drawing the battery is very inconvenient. Okay, the pictures that we draw to represent a circuit are called schematic diagrams. And so this is what a battery would look like. Really, and to be more precise, this is a cell, but I'm generally going to draw my batteries this way. I'm generally going to draw my power supplies this way. I'm not going to be super precise with how I draw the power supply, but people in circuitry, they're a little bit more precise with this. The long one is a positive, the short one's a negative terminal of the battery. And then I'm going to hook it up to a light bulb. And so if I want to measure voltage, I take my meter and I put the positive side of the meter here, and then the negative side here, this is called parallel. This is called a cross. Okay? And you measure the voltage. And this light bulb is called a load. It doesn't have to be a light bulb. Whatever the load is, it's represented usually with this squiggly line called a resistance. Okay? So voltage is easy to measure because all you do is hook up things up across. Resistance is also easy to measure. Resistance is a device that opposes current. Your body opposes current going through it. So on these meters, you put the wires in the same two terminals, essentially. One that says common, which is usually connected to ground, and then there's one that says volts and ohms, like that. And then, trying to find the ohms on here. You'll see the ohm symbol, so you turn it to the ohm symbol. There you go, yeah. And you'll see they're very similar, right? The green one I have is actually a little bit better than what you guys got. This was too expensive. This is what I wanted to get you guys. Anyway, so you take the wires, you can measure the resistance of your body. Okay? I can just hold one terminal in one hand, the other terminal in the other hand, and measure the resistance of my body. And depending on how good your contact is, it's going to vary. So mine's varying a lot. In fact, the batteries. You can see how it's changing all the time. I don't have a constant contact. So you can actually measure the resistance of your body. And it's usually going to be in megohms. You can also measure the resistance of the light bulb. Now, when you're measuring resistance, never, ever, ever, ever have the component in the circuit connected to the battery. You take it out of the circuit. So I can measure the resistance of the light bulb just by basically, I'm going to get a different wire because this one's too short. All I got to do is take the two terminals that come from the meter, and I just connect them to the light bulb. And this will say, usually it's about a couple ohms. Okay, that's all you got to do. So to measure resistance, you have to take the bulb out of the circuit, cannot be connected to the battery, and then set this on ohms. And measure resistance. That's it. So measuring resistance is easy. Measuring voltage is easy. It's pretty straightforward. Okay? You just put things across. The hard one to measure is current. By the way, when you're measuring resistance, it's actually running a current through your body, but it's not a large current. You don't feel it. All right, but it is measuring a current through your body, and it has a voltage. So the voltage divided by the current is the resistance. So that's how it's measuring your resistance. Current is very hard to measure when you're learning. What I mean by that is students will generally do it wrong and they blow a fuse. Okay? So in order for you to measure current, you actually have to have the same amount of charge going through your element as you do in the meter. If I put the meter in parallel across like this. Now what I've done is I've given the electrons two different paths. It's like when you have water flowing in a pipe, you've given it two different paths. Okay, when you put things in parallel, you're giving something a different path. So if you're giving them a different path, are you going to have the same amount of current going through the bulb? No, because you're going to think about water. Some of the water is going to go this way, right? So you can't do that. So what you have to do is disconnect your circuit and put the meter in your circuit so that the same amount, so that you have no branching point in your circuit. So now, if you're thinking of water going through a pipe, and you put like a flow meter, whatever goes through here goes through here. So whatever electrons go through this bulb go through this. This is called a series connection. So you have to have them in series. Okay? Meaning you have to put one after the other. Okay, so this is a schematic diagram of what it should look like to measure current. Okay? So you have to have the meter in series with the element to measure current. So you'll get the current through this guy, and it's going to match the current through this guy.
And it doesn't matter if we put the meter before or after the resistance?
No, it doesn't actually. Yeah, you can put it. You can put it anywhere here. As long as you don't have a branching point, you'll be fine. Okay. So the other thing about the meter is it's designed so that when you put it in the circuit, its resistance is really low, so it doesn't change the properties of your circuit. Okay? It doesn't change the properties of your circuit. It doesn't change the resistance. That's important. As a result of that, because it's hard to make that resistance low, to measure current, there's multiple settings on a meter. To measure voltage is generally one setting. Okay? But to measure current, there's multiple settings because you want the current, you want the effect of this to be really small. However, you also want it to be able to sense the current. And so what happens is when the current, if the current that you're measuring is smaller, you actually have to put a bigger resistor in here to get a more precise measurement. Okay? So when the current, you're measuring a small current, the resistance is actually a bit larger. When you're measuring a large current, the resistance of the thing is really low. It's low compared to the circuit. So there's multiple settings for current. This one doesn't have it, but if you look at yours that you have, I don't know if you can show, Sean, you can show that red one. There's 3 settings for current where you see the letter A. Okay? So there's 3 settings, and then there's one called that says milliamps and microamps. So you're going to put one of the cables where it says COM, and the other one where it says milliamps and microamps. Okay, and so that'll give you a range. It'll allow you to measure currents from 0 to 200 milliamps. If you're going to go above 200 milliamps, then you got to take this one and put it in the 10 amp scale. And then there's a 10 amp scale on that multimeter. Okay? And you use that one. So when you do this lab, thanks, Sean. When you do this lab, what you're going to be doing is you're going to be measuring current. You're basically going to be measuring the current through one of these bulbs. You have to show me in the video that you know how to measure the current through the bulbs. You can have a battery, a bulb, and this. So you're basically wiring this up. And you're going to show me that you know how to make a proper measurement on the right scale. So you're going to actually estimate the current in your circuit ahead of time. So you're going to measure, or you're going to assume a resistance for the bulb. I think it says 1.5 ohms. The battery is about 1.5 volts. If you want to be more exact than that, you can measure the battery voltage. It's up to you. And you're going to take the voltage divided by the resistance. That's going to give you the current. Based on that estimate, you're going to hook everything up to measure that current. And if it's too high, or if the current's too low, then you want to show me how you can safely switch to another scale. Here's a problem. When you put this in your circuit, if you have this wired, and then you start turning, and you pass one of the low current scales, what do you think might happen to your fuse? If I turn this, let's say the current's 200 milliamps, and I turn this, and you get to a scale that's microamps, what do you think is going to happen?
Are you going to blow it out?
Yeah, you're going to blow a fuse. So what you want is, before you turn this on, remove one of the wires from the circuit and turn this to the right scale, and then plug this back in. Okay? Or, I could disconnect one of these, put this to the right scale, and then plug that back in. That way you won't blow a fuse. And every time you switch, you pull this out and go to the right scale. Otherwise, you're going to blow fuses. Okay? You do have an extra fuse in your kit. And by the way, to change the fuse, you have to take that red plastic off and then take the screws off in the back. And you'll see the fuse. You might have to use, I don't know, your fingers, you might not be able to get to it, but you have to pull the old one out and then put the new one in. The fuse is about this long. It's you can see right through it. Okay. Actually, that's not the fuse. Yeah, it's you actually have to open this up. There's screws in the back. You got to take the red protective cover off first. Okay, these are actually easier. The fuses on these are actually easier to change. The ones we used to have to give the class a small one. The fuses on those are very hard to change. You have to completely take apart the meter to change the fuse. Okay. I need for you to be in contact with me as you're doing this. So just contact me. You can. I'll be here on Monday if you have questions. You might not get started on this right away because you're still doing it properly, the charge lab. One of the reasons why I'm doing this early is just because of the way we're doing things online. I am going to be here on Mondays, so if you have questions about how this works, come and see me. Next Friday, I will not be here. Professor Shakal will be handling this lab, and so she will be answering your questions on either the Chapter 27 homework or on how to wire this. Okay? Do you have any questions so far?
I have a couple of questions.
Go ahead.
So we have the properties of charge lab due next Friday. Is this lab due the Friday after that, or 2 Fridays after?
I think the Friday after that, because that's October 3rd. Right. Next week is the 25th. Actually, the 25th is a Saturday, right?
Yes.
Okay. So this is due on a Saturday, and then this is due on the following Friday, if I remember correctly. We'll see how this goes. I mean, I might be able. I mean, I can maybe add a day or two to that. That's fine. Okay, we'll see how that one goes. But this is a very fundamental lab because you're going to be doing a lot of circuit labs this semester. And then the last 3 labs of the semester, you're going to be doing the circuit labs in person. So you actually need to know how to use this. This is not the most important tool you use in circuits. There's one that's more important. It's called an oscilloscope. Okay? Because really, you can only look at voltages that are constant in time. If the voltage varies with time, this thing is kind of useless. An oscilloscope will help you look at voltages as a function of time. And we'll do those later. Okay. So let me show you real quick the module because there's a simulator in there that I would like for you to see. Just give me a second. I have to move this window over. Okay. And okay, so I'm going to look at we're looking at the modules right now. My other screen's really far away, so it's hard for me to see. Okay, so look through the modules. There's this simulation. And this is for you to play with because you can build this, you can actually build the circuit that you're going to be playing with on here. This is I think it's kind of cool. I can take a battery and a light bulb and I can wire this up. So the light bulb goes on. I can actually put 2 batteries in series. Let me get rid of this thing. Let me get another battery. If I put 2 batteries in series, what is going to happen? Oops, I didn't connect something. It's a lot brighter, isn't it? So this is called 2 batteries in series, one after the other. Okay. So if you want to put a multimeter, if you want to measure current, this should help you do the next part, the current measurement. And that shows you the current right there. So notice I put it in series. So now translate that into what you're going to be doing in the lab. Translate it in terms of what you're going to be doing with this guy. Okay? You can play around with it, put batteries in series, battery in parallel before you do anything. So that's why I put that for you, so you can play with it, because it's much harder to do this lab online than it is in person. Okay? All right, let me go check the chat real quick. I didn't see the question in the chat. No partners for this lab. This is individualized. Okay? It won't be until the last 2 labs of the semester where you're going to have partners again. Okay, this is individualized because each person has to know how to use this. Okay, so let me go back to the modules. I also have some videos, and this is where you're going to get to know this guy called Electro Boom. He's a famous person on YouTube. There's videos on here on how circuits work, and there's this person named Electro Boom, which I like a lot. He's funny.
Yeah, he's pretty good.
You've seen him? Okay. So there's a couple on there. So the ones I've put on here have been properly captioned. He has a lot more. The college frowns upon me putting things that are not properly captioned. Okay. But he has one on series and parallel. It's not properly captioned, but you might want to see that too. I mean, anything about circuits, he does. I mean, real basic stuff, which is very nice. It's just that I can't put all the ones that are not properly captioned. Some of them are captioned in a different language, not English, so it's not going to help us. Anyway, so you should get familiar with his videos because he's funny, he's entertaining, and you'll learn from him. Okay, questions?
Someone asked if we can have partners for the properties of charge lab.
Oh yeah, for the properties of charge lab, yeah, you're allowed to have partners. The only thing about it is that I would like for you to, if you have a partner, everybody should be involved in every part. Okay, that's the one, and I think I mentioned that when I discussed the lab, and I think it says that in the lab itself. Okay, because otherwise you're gonna have one person doing part one, another person doing part two separately. Everybody needs to do every part of the lab. Okay, because otherwise, I mean, what's the purpose? Yeah, the property of charge lab is one of the few ones you're allowed to use to have a partner. And then we're going to have two at the end of the semester where you're allowed to have a partner. So there's going to be a total of 3. Uh-oh.
Professor,
Yeah.
I don't know if you said this already or if it's in the syllabus, but what is the multimeter quiz?
The multimeter, okay, let me go back to, it. Let me show the exercise. Hold on a second. I have a computer across the room. I don't know why it displays that bad. Okay. Let me open up the file. And it really shouldn't be called a quiz. It should be a a skill demonstration. So this is it. And what you're going to do is you're going to wire. That's why I've been showing you. I've been showing you this. This comes in your lab kit. You're going to be wiring this. The instructions are in that file. So you're gonna make a video demonstrating that you can do steps 1 through 6. Does that make sense?
Yeah, it does. Okay, thank you.
So that's the quiz. That's all it is. So 1 through 7, sorry. So you just got to do steps 1 through 7. So the video won't be that long. Okay. What I don't want you to do is try not to send me a video of you doing No, I actually want to see you doing the wiring. I want to see you doing some of the wiring, so I know that you know what you're doing. Okay. But if there are things you can cut out, that's fine. Although I can run the video in double speed. So it might, I guess it might be 10 minutes long, this video. If you want to make it in parts, you can make it in parts, however you want to do it. Okay. But you have to demonstrate to me that you can measure current, you can measure voltage, and you can wire things in series and parallel. That's why I showed you that. That's why I showed you that simulation, because you can wire that in the simulation. And once you know how to wire it in the simulation, then doing the real ones, no problem. It's easy. Okay. Although measuring the current still is a challenge. I will say that. I mean, the simulation can go only so far, but if you want to measure current, you'll get a good idea with the simulation. But you know, to do it with the real meter, it's still it's still different. Okay. So you're gonna have to, for that first one, you're gonna have to have 2 lamps in series and 2 batteries in parallel. Okay. Other questions?
I have a question more general about the class. Did you send out the recording from student hours last night?
No, I have not, and I need to do
Okay.
that. I will do it if I get a chance after this, after our meeting. I'll do it then, or otherwise I'll do it after my 11 o'clock class. Okay.
Thank you.
Anything else? Okay, I want to say a couple more things. I'm not sure why my screen looks weird like that. Hold on a second. I want to say a couple of things about circuits. So, here's some terminology. Let's take a look at this circuit. The circuit shows the power supply voltage, and the rating on the battery is called the EMF. That's the battery, that's the rating. All batteries have something called an internal resistance, and they get worse as the battery get older. So what that means is, even though that says 3 volts, what's across the resistor, the load, is not going to be 3 volts. That's because a real power supply has something called an internal resistance. It's almost as if there's another resistor in the circuit. So the voltage across the resistor the big R will be less than 3 volts. And that voltage is called a terminal voltage. We're going to assume in our discussion that the wires have negligible resistance. Okay. Here is a circuit with a real power supply, a real battery, where I put the internal resistance in. I'm not always going to draw the internal resistance, little r, in our circuits. We're going to assume the power supplies are going to be ideal. Each closed path in the circuit is called a loop. So you see in that picture something called a loop. So there's 3 loops in that circuit. Can you see the 3 loops? There's the one containing the 2 resistors. There's the yellow one that you see there, and then there's the outer loop. And any one of those can be used to analyze the circuit. Oops. The points where current can branch off are called nodes or junctions. Okay? Where the current can branch off, they're called nodes or junctions. Here are 3 power supplies or 3 batteries in series. By the way, those 2 resistors, how are those 2 resistors connected? One across the other. That's called parallel. And when they're in parallel, they have the same voltage drop across them. So let me explain that real quick. Let me go up to the board. So if I have a load, here's a battery. And I hook up, this is a resistor. Could be a light bulb, could be anything. If I hook up another resistor, in the same way I would hook up a multimeter to measure voltage across this. This is called parallel. And the reason why they're in parallel is that the voltage here are the same. And think about it. If this is 3 volts, this is 0 volts. Let's pretend that's 0 volts. I grounded that. Then this point over here is 3 volts. This point over here is 3 volts. This point over here is 3 volts. This is 0 volts. We're pretending the resistors have no, the wires have no resistance. What's the voltage drop between these 2 points? What's 3 minus 0? It's 3. What's the voltage drop between these 2 points? It went from 3 to 0, just like here. 3 minus 0 is 3. 3 minus 0 is 3. So these have the same voltage across them, and so we say we're in parallel. So when you put a multimeter across, the voltage across this guy is going to be the same as the voltage across this guy and the same voltage across that guy. And you have a branching point. That's the other key to knowing things are in parallel. Now you have 2 paths for the electrons to go, right? The current goes this way, and then it branches off either this way or this way. By the way, the voltmeter is designed so it has an essentially infinite resistance. So almost nothing goes this way. It's like having a T, if you have a pipe with the water flowing here, and I put a valve here that's closed. Okay? Same idea. So the voltmeter is essentially like this with the closed valve. Now the other case, I have 3 batteries. And I have, let's make this 0 volts as a reference. I grounded it. That's what I did in the picture. And each of these batteries are 1.5 volts. A battery is a device that maintains a potential difference between its 2 terminals. But what value any one terminal is arbitrary. So if I connect the negative side to 0, this side's 0, this is 1.5. If I connect the negative side of the second battery to this guy, this is 1.5, and this is 3. And then this becomes 3, and this becomes 4.5. And so this point's at 4.5. This point's at 4.5 volts. And this point is at 0. So the voltage drop across the resistor is 4.5 volts. And if the resistor was 10 ohms, then the current, if I use that equation, is going to be delta V over R. It would be 10 ohms over, 4.4 volts over 10 ohms. Like that. These devices that I'm putting in my circuit are ohmic. They obey Ohm's law. So that means that over a range of voltages I apply to this, the resistance doesn't change. The ratio of delta V to I stays the same independent of the applied voltage. That's something that obeys Ohm's law. When it starts changing, then it doesn't obey Ohm's law. In other words, you don't get that straight line. You can still define resistance for that, like a light bulb, but you don't get a straight line. Okay? I want to introduce. Go ahead.
Could you explain to me why it jumps from 1.5 to 3 to 4.5 again?
4.5? It didn't come in clear, sorry.
Sorry, could you explain again why the voltage jumps from 1.5 to 3 to 4.5 again?
Oh, from here to here?
Yeah. Could you just explain why it jumps like that again?
Well, because if you have a battery, all we know in the battery is that there's a difference of 4.5 volts here, but it's what either side is arbitrary. Just like gravitational potential energy. What's the potential energy on the surface of the table? Do you know what it is? You don't, right? It's arbitrary. It depends on where you define your zero. I define my zero here. I grounded it. And so then I connected the negative of this battery to the positive of the previous one. And we know that's 3 volts, so this has to be 3 volts. And all batteries maintain a potential difference of 1.5 volts. So 3 plus 1.5 is 4.5.
Oh, okay. I got
Okay. Yeah, so the actual value of V is arbitrary on either side of this thing. You just got to define one end, and then you got the other end. Same thing like potential energy. And you'll find that electrical potential has some similarities to mechanics. We don't talk about gravitational potential, which would be gravitational potential energy divided by mass. We don't talk about it because it's not very useful. But that concept does exist. Here it's very important. Okay. I think what I'm going to do, I think I had the homework due on the 24th. I might have to give you a couple more days. Let me think about it. Okay. I ran out of time. I was going to introduce one more concept, but that's okay. I think I'll have Aviva introduce that concept to you guys. Okay? All right, that's in then. Have a good weekend.
Well, thank you. You too.
All right.
Thank you.